Next, I want to implement FizzBuzz in Plum, just to have that done, you know, because that's kind of a beginner project usually. Which means I'll actually have a function, I guess, FizzBuzz, that takes an int, like starting at what number you want to do stuff, and it's going to return a task. And we'll check if, well, first of all, if we should even do anything. So I think, you know, if I is larger than 100, then we don't want to do anything. Then we'll just I don't know, we'll exit actually. Yeah. And let's do that with this kind of backwards syntax. So if I is larger than 100, then we want to exit. Otherwise, nice early return. Otherwise, we check if I is, well, I mod 15, I guess, is 0. And if it is, oh, this is nice, then we'll just do print FizzBuzz. Let's do it like that. FizzBuzz, and the then lambda will be actually a lambda that you can call that then calls this lambda recursively with I plus 1. Alright. And then if it's divisible by 3, we just print fizz. If it's divisible by 5, we print buzz. Otherwise, we print the number itself. Oh, actually, you know what? Let's... I'll have a next as a lambda that calls this thing recursively. Yeah, that makes sense. And then we can just factor that out and call that next. Alright, and then here we just do I.format. Yeah, and then let's just call that FizzBuzz starting at 0, I guess. And let's see how that goes. Ooh, something is not imported. Yeah, the larger than function. Taking two ints. I guess that makes sense. Then the equals function. Then if, oh, I think we actually need to export that from the bool module. So if bool, and it takes some t, and then a lambda that returns a t. And in the standard library, I think we'll need to import that in here. Yeah. All right. And then in the bool, we'll need the call function from the call module. Yeah. Yeah, like that. Okay, what do we have here? Lots of leaked memory, apparently. That's not good. that was something that looked sort of promising, I guess. So 0 is divisible by both, so we do FizzBuzz. Then 1, 2, 3, 4, buzz, fizz. 6 is divisible by 3, and 7, 8. Fizz, buzz. What's going on there? How do ints work? So we are formatting an int. Is the int negative? No. So then we concatenate either an empty string if it's less than 10, which let's say the int is 8, 9, 10, 11. Let's say the int is 11. Yeah, then this will be false. So this will be int divided by 10. That will be 1.format. And then int mod 10, which will also be 1.format digit. So this right here will call int divided by 10, which is 1.format, which will call this recursively. Still not negative. Is int less than 10? Yes, 1 is less than 10, so we just concatenate the empty string and the 1 formatted. Yeah. And in both cases we should just evaluate to the string 1. So then these should be concatenated. Alright. Why is that not working? How is FizzBuzz not working? That's Also, why is this happening? Let's see if that actually happens with smaller tasks as well. So if we just want to print something, print hello world, and then we want to exit. This was supposed to just be like a 5-minute video or something. Is that supposed to be a lambda that returns exit? Okay, that already leaks memory for some reason. I guess let's print the allocations and deallocations, because my thinking is, you know, I know that there's a memory leak somewhere. Maybe that same memory issue is the one that makes these numbers up here print really weirdly. Yeah. So let's try to fix that. All right. First step, debugging memory allocations. So this would be this one, where we want to just print all allocations, please. Boom. Yeah, this one, allocated and free. And that means we need to build the VM, so that we can then rerun that and we can see lots of stuff. All right. Actually, 2 things that are not freed. That's unfortunate. Oh, actually, no. I think this one is freed. This is just the hello world string that the program itself does not allocate, but our Zig VM is responsible for freeing this string, and that probably happens. But this one right here, this is I think the closure of the else of the exit function. So to create this lambda here, we need to have a pointer to a closure. The closure doesn't contain anything, doesn't need anything. Yeah, later on we'll kind of have to optimize that out, I guess. But for now, that's just a pointer to an allocation that contains nothing, only a reference count. So size 8. First step for debugging these sort of memory leaks and so on is enabling some of the running in here. So yeah, the yogurt works, I guess. The pudding is the one that introduces dupe and drop instructions to neutralize gouge. So let's actually try to run that and see, and maybe even print that, sure, why not? And see if that passes all the, like, that's a very strict execution, and you know, interpreting that compiler stage directly in a very strict way that finds memory leaks and so on. Okay, that compiled apparently, which, okay, yeah. Oh, it does not detect leakage, I think. Only, you know, if you access something without it being, yeah, so this results in this print thing with a then blub. Yeah, I'm not too sure about that. Let's see, this run, does it return a pudding result or something like that? Pudding heap, pudding value. Just returns a pudding value. All right. Ah, pudding result. Yeah, exactly. All right. So that contains a heap and the actual value, and the heap, there we can do drop, I hope. Yeah, we can do drop. Okay, so I think what we want to do here is pudding drop. Yeah, we can print the result, but then yeah, then we want to drop the value at the entire value. Not sure what that one. Result.heap, ensure everything freed, something like that. That doesn't exist right now. Let's add that. A list of pudding value data that contains a ref count. All right. let's just print, like dump the entire heap. Just to be sure. Okay, that actually works. That is kind of surprising to me. Although we did drop the entire value here. Well. I mean, we know that this value is supposed to be an enum. Yeah, with the name something, name print, and then a payload, which is a then with a message. So let's actually do a bit more. Let's say, we want to keep the then lambda because we want to call that. So let's actually do dupe the result dot value. We know that's an enum, and then that enum has a value which we know is a struct. Oh, hang on. We need to get those from the heap, right? Yeah, get. Oh, okay. So let's do. Introduce even more stuff. So result.heap. All right. So we get the value from the heap. Then we want to get the. We know that's a closure. We know that that's an enum first of all. So res.enum.unwrap. All right. And let's do that in here, I think. Enum.unwrap. All right. And then we know that that is a struct that we can then unwrap again to get a map where we can do get the field then, that's the lambda. And then we want to dupe that lambda and then free the entire result value. And that should basically free everything of this enum except this lambda. So that should free the enum itself, it should free the struct, it should free the message including this struct and the the bytes and all the individual bytes as well, and so on. But this lambda here, this is the only thing that we want to keep alive. Let's see if that works. Like, this should now crash. This should say, hey, there is memory being leaked. What's going on here? We have enum.unwrap.value. That's the payload that we want to get. Okay, memory leaked. That's nice. Like, that's what we expect. So what memory is leaked? First of all, we have bytes. These have ref count 0, that's fine. Ref count 0, ref count 0. Here, this is the actual enum and the struct ref count 0. Amazing. But then in here, this is the lambda. And, well, I'm actually not sure what exactly is going on there. The lambda, let's print a bit more for lambdas, I think. So when debug dumping the entire heap, yeah, when we have a lambda, let's actually print the closure. Oh, what is that? That's not a thing, right? Closure? I don't think closures exist. And we just have boxes. So that simplifies stuff. Yeah, let's just run that and see what happens. Oh no. Value dot index. In here we always do dot index to print the actual number, which makes sense, I guess. Kind of more explicit. Do you actually want to print the value? Then it needs a heap, or do you want to print just the number? Yeah, 230. Case closures. Closure. What is closure? What are we doing here? We have a pudding expression. Is there an expression, pudding expression dot closure? There shouldn't be. There is. That's a bit surprising. Alright. Okay, maybe we do want closures still in here. Which kind of sucks, but let's not have closures in here, but instead let's say that these just create boxes. Which is what happens under the hood anyways, so yeah, that does seem more clean. Let's see if that works. Ah. You know, when you do undo, but things, you change your mind, and meh. Although that's not great. Okay, but that compiles at least. All right. Oh, this is surprising. So we have this enum. Fair enough. And then you're ignoring all these ref count 0 things. We have a closure. Closure 19, which is a box of some other thing, which then is a closure, has as the closure this one right here, and that has this one. What is going on there? Let's look at the source code again. So we do this, we have print in here, and that, you know, executed completely. So that's an enum with print with a message inside, and then is this closure, and that's just an enum, and that's just a closure. There is nothing. I don't get that. Why are there two closures? Kind of indirections. Yeah. That enum previously, you know, that contained the then closure, which was a lambda that contained a closure that captures another lambda with an empty closure. What? Let's print pudding. But hang on, we do that already, don't we? Yes, we do. All right. So I guess this is the main function. Oh, it's because of this cast. Let's see. We drop the argument, fair enough. We create a string, okay. We box this empty closure. That makes sense. Huh. We never have a closure instruction, a closure expression in the pudding, because we just call the box built in, right? Is this ever used? I don't think so. I think this is just there. Hang on, we can check, does the yogurt have? The yogurt does not have any closure expressions. Okay, so I think this shouldn't either. Like, neither should this. Yeah, perfect English. Alright, and that makes the run pudding simpler, because then in here we don't need to care about that one. And yeah, that's about that. And then in the next compiler stage, pudding to pesto, exactly. We don't need to care about closures. Beautiful. All right. That does not work because of some helper function. Yeah, for printing pudding, that makes sense. Alright, and that compiles, that's nice. Alright, anyways, so in here we create an empty struct on the heap. We box that. Then we create a lambda with that closure. With this code. 1160 something. Oh, and this lambda never drops the closure, I think. Does it? Anyways, what happens here? We then call box another time with this lambda. So we can box that lambda up so that we can then do this. Oh, that's strange. Right, hang on. We are casting. Oh no, that's just the type. I see. We are casting this exit thing to this thing. All right. Yeah, that makes sense. Oh, I see. We have a lambda that creates. We have a lambda that returns only the type exit. And we need a lambda that returns a task. So we build a kind of wrapper lambda around that. That captures this inner lambda returning exit. And the outer lambda then, you know, it just calls the inner lambda. All right, yeah, and that's defined down here. Fair enough. Okay, yeah, that calls unbox on the thing that's given there, on the nothing, and then it on the captured lambda. Oh yeah, I see. Then it just calls that lambda. Yeah, and then it switches on whatever that lambda returns. It can only return exit, so I mean that switch is basically useless. But anyways, and then it creates this exit variant of the type task. I see. Right, yeah, so I'm wondering though, this lambda here takes ownership of the closure when you call that. You know, this down here seems totally fine. You know, we have this lambda that we can call that sure captures another lambda that then captures nothing. Fair enough. Actually, can we call that? That would be super nice. Let's do in the run pudding. We do have a run function in here, I think. Run pudding expression. Run pudding body with some arguments. Alright, that's interesting. Oh, that's even better. Run a function. With a heap and a stack. And args and pudding. Alright. And then we have this one. I think let's actually do run. I'm not sure. Running a lambda, basically. That's the idea. Maybe let's not do that. Let's just run the... let's do something like that. So in the main file in here, we get the lambda. We kind of drop everything except the lambda, which we dupe before that. And then we say, you know what, let's call that lambda. Let's do, not putting the entry pointer run, no, but let's do, this is the print payload. And this is the lambda. And here we dupe the lambda. All right. And then here we do lambda dot. Heap dot get lambda. We know that's a lambda. And that means that this has a function in there. And then we can run that function with no arguments. And the pudding and an empty stack and a mutable heap. And then let's print what that lambda returns. Oh, actually, I think the closure has to be an argument. Yeah, that makes sense. So the closure, oh no. The closure is basically just this one. Is this horrible? Kind of. Doing that 2 times, yeah. Make this part. Temporary code. It's just for debugging the memory leak, so. Okay, what do we have here? We can't print a value, that's correct. We want to print not a result, but we want to, we can print a value if we also have a heap, right? Isn't that how that works? It is. Okay. So let's see if we call that continuation lambda, if we still leak memory. We shouldn't. But we do. Okay. And look at that. That single lambda is still in there. That. Alright, why is that happening? So I think in lambdas, they don't clean up their closure. They should take ownership of this one, but they don't. Yeah, this is just making things sure. Yeah, we are in the pudding where we have explicit dupe and drop instructions, and here we have a lambda that takes no arguments and returns exit. Well, lambdas taking no arguments actually, lambdas always take one extra argument, which is the closure. So this lambda unboxes the closure. Makes sense. It doesn't contain it, it contains an empty struct, no data. Fair enough. And it doesn't need that, so it just drops that data immediately. Then it constructs what it wants to return. However, it should also be responsible for freeing up the closure. Why is that not happening? That's actually kind of weird. Let's see. So the error is definitely in the yogurt to pudding. Kind of pinpointed that to one compiler stage. That's pretty cool. So we do have this require in here. And when we convert a body, a yogurt body, to the pudding, we track which IDs we need later on. Oh, hang on. Actually, this we call this built-in unbox function. Passing ownership of that closure to that unbox function, which gives us a struct and frees the thing. That should actually work. So hang on, when we run the pudding in here, I think we don't handle that built-in correctly. Yeah, functions take ownership of the built-in functions. They take ownership of the arguments, of functions in general. Yeah, for ins, that doesn't matter. I mean, hang on, actually, yeah, it does matter. We get the int from the heap, and then we drop that. We get the int, or the byte from the heap, we drop that, and so on. For boxing stuff and unboxing stuff, we need to do the same thing. Can't just take that and return that. We have to, well, when we want to box something, so we create a new heap thing, heap box of that thing. Okay, that's actually correct, because the box takes ownership of that value. But when we unbox something, we actually want to get the payload. That is some yogurt value, and then we want to dupe the payload, because that's what we are going to return, and then drop the underlying, drop the original box, basically. We can make it even more readable using this. Look at that. We are given a box. We get the payload value, and then we dupe the payload. So reference count of 2, possibly, possibly more. And then we drop the surrounding box, which drops, the payload's ref count again. So that kind of cancels out. The payload has the same ref count as before. It's just that the surrounding box no longer exists. That is freed. Which means in here, this should no longer leak any memory. Now that's only the interpreter of the pudding. The Zig compiler, that's not affected by that. That should still... Oh, look at that. Oh, is that any different than before? That's actually... That's interesting. We have this. We have some sort of... Hang on, we have some closure. Let's see. This is different than before, I think. Let's scroll up a bit. Yeah, this one. Yeah, this is where that started, and this was the previous run. And here at the end, yeah, it's a memory leaked. Boom, and all of this was leaked. Yep. This closure was leaked. That inner wrapped closure was leaked. The that lambda with that closure, that lambda with that closure, that all of that was leaked. Now things are a bit better, at least, We, like, the inner lambda is freed, and the inner, like, the closure of that one is freed as well. But in here, this lambda itself, that's still alive. Oh, I see. But that's actually expected, I think. Yeah, a lambda only takes ownership of its closure, not of the lambda itself, because I mean in later compiler stages that doesn't even make sense. Okay, but this does seem like it makes, like this code makes sense. Here we, rather than just running the lambda function directly, we should actually get a reference to the closure. Heap get lambda. We know that's a lambda, and that it has a closure. Oh, look at that! We can even do that. But then we can do heap dot. We can kind of dupe the closure. Oh, actually, let's get the function out of there as well. We're getting the function and the closure, then that's everything that the lambda holds. So we then dupe the closure and drop the surrounding lambda, because we already have the function and the closure. Yeah, and then I mean this then returns a result, which is the exit enum, which we are responsible for freeing, which we don't currently. So it makes sense that this exit enum, as well as the payload of that, is still still has a reference count of 1 and is not freed. Yeah, that does seem reasonable. Okay, and if we free that result as well, then everything is freed and stuff is okay. Alright. So if we do that, freeing the result, then it should not say memory leaked, but instead the error is somewhere else. Well, yeah. Did that error of with box and unbox, did that maybe happen somewhere later in the compile pipeline as well? Like, where are the currently we are in the pudding, where the pudding built-ins, they still contain box and unbox. Then we have the pesto as the next compiler stage, which is somewhere else. Where's the pesto? Here. Yeah, here we don't, like, we no longer have the box and unbox things. Instead, these become load and new and load, I think. Which means, how are those compiled actually? Putting to pesto. Let's look at the built-ins. Yeah, calling a built-in, calling the box built-in. We are given ownership of the payload. Alright, and we just do build it up new, which allocates a new object for that. New allocation, memory region. Okay, with the unbox thing, we get the box first of all. That's nice. We get the inner type, which is, yeah, exactly that. Fair. And then we load that. Mm-hmm. All right. Let's factor that out. Like that. Yeah. And here we drop the box. Which oh, I see. Yeah. Freeing stuff is something completely different, I think. Or is it? Do we have... What is the... What do dupe and drop instructions do? They do builder.dupe and builder.drop. Yeah. So here it says builder.drop of that surrounding box. But then isn't the inner value dropped as well? Even though we want to return that later on. I think we'll need to do builder.dupe mapping.get. Oh. No, dupe the inner one with the inner type. And then drop the outer box. Because if that inner thing contains other pointers, look at that. No memory leaks. That is quite cool. That's super cool. Alright. Another bug fixed. That's cool. Let's first of all commit some stuff. Let's say, putting that FizzBuzz to the side, kind of just, yeah, this is like general refactoring, I guess. And yeah, we no longer have closure and stuff in here. And putting to pesto also becomes a bit simpler. And then run pudding becomes simpler because we no longer have closures. Yeah, that's kind of independent of that. Let's yeah, let's do that. Simplify pudding, and then a separate change is this one, basically. Doing detect memory leaks in one pudding, boom, and then, by the way, this, we don't need printing of that, and then this is actually fixing the bug. Fix memory leak, boom. I mean, you can really see the progression, simplify pudding, detect memory leaks, fix memory leak. Nice. So now let's try the FizzBuzz. And see if that works. change the zig compiler, the zig VM, so that it doesn't print all the allocations, because I think that's kind of we're still leaking memory for this. For some reason. I don't get it. Okay, but printing these strings works now. I mean, that's an improvement, I guess. Yeah, let's kind of fix the zig VM quickly, and then I think that's it for this video. Yeah, let's remove these debug prints and rerun them quickly. Yes, and look at, oh, I see. Build the zig VM. All right. Now we should have glorious FizzBuzz at the beginning. Oh, look at this. Look at the FizzBuzz. 30, yeah, amazing. Wonderful. Yeah, memory leaks, more memory leaks. Well, problem for later me. And for later you, possibly. So, see you in the next video.